Okay, I thought I'd do a Functions 12 course, and I can't stress this enough, okay? One, the shortest route. If you're looking for the shortest route through this course, it is not delaying to the last minute. If you wait to the last minute, you will find yourself burdened with such a feeling of dread that you will fail, and then you will say to yourself, I can't do math. Well, the truth is, everyone can do math, so you can do math. So break open the textbook day one and start with the questions. That's the shortest route. Ignore the lectures, whatever. The textbook has all the examples you need. Just go straight to the questions, and if you can't do the questions, go backwards in the text, and there will be an example. You mimic the example, and you'll be able to do it. Your teacher might fine-tune for what he or she is looking for, but this is the shortest route. The shortest route is not waiting to the last minute. It is not copying down formulas. That's disaster. It is practice, practice, practice. Math is like tennis, soccer, or any sport. It's kicking the ball that will get you there. Watching the ball will not. So what you should do to get great marks, realize that the classroom is just the intro. It's at home work is far more important. Save time, do as many questions as possible. Reading is okay, but actually doing the puzzles is key. Morning's the best time to work. You've probably noticed late at night when you try to study, your head drifts and you reread the same sentence 3 or 4 times. Why bother? Wake up earlier, have a good thing of food, pour yourself a coffee, nice and quiet, and study. Quiet is also good. That's why people study in libraries. Take great notes. Why repeat the thing over and over again? Like whatever you study this morning, if you don't write it down, you will forget 3 days from now. Take great notes. That way when you review the notes, it will trigger. And also, science has revealed that when you take notes, you remember something longer. That's why class and school makes you take notes. There's a science behind it. Write down the concept, one solid example from the textbook, and then answer 3 or 4 standard questions that you think will be on the test. Do a little math every day. I can't stress this enough. You'll save yourself so much time. If you do a little math every day, if you wait till Sunday, you're going to be so overwhelmed and texting friends and frustrated, and it will be like trying to squeeze toothpaste, a whole tube of toothpaste into your mouth and talk. You'll just find it so overwhelming and impossible. It's not going to happen. And finally, use tools. You live in the internet age. There are so many good things out there. Freeze the frame anytime I'm talking too fast. Freeze and write these down. But Desmos, fantastic. It lets you graph whatever thing you're studying at the time. Okay? Boom, there's a graph. And it knows function notation. And it knows translation. So if I make my g of x and make it 2 times f of x, it knows how to do it. It knows it's a fantastic tool. The next tool is Symbolab, and you'll find that sometimes it blocks one of the answers. I found the secret is to copy and paste where it blocks because they're trying to make you pay, right? It'll still give you the answer. It might not show you the steps. So when they block one of the steps, just copy and paste the step just before that, put it up here and hit go again, and eventually they accidentally reveal it. Mathway is also good. You can punch in the equation and click solve. Here I've punched in this equation and it's giving me the factors. Okay, and then finally, also you got to realize there's calculators out there. Calculate quadratic formula calculator. Okay, boom, there it is. Suddenly you can, I want you to learn the quadratic formula, but you know, your hand calculator is going to do more errors than this calculator is. So long as you understand the concept and know how to do it, this is a great tool. And finally, YouTube. YouTube, you're going to discover there's a gazillion people who can teach you a method faster than I can. So you want to save time, listen to that. Now also, as I'm doing this, I'd like you to pause the video and do the questions, okay? So here's what you do. You break open chapter 1, and it actually helps to read the review of the chapters overall up above. But anyway, chapter 1. They're always going to run you through the concepts you need for this chapter. These concepts are often from the chapter before or even from last year. So in this case, last year, they're giving you a function formula. They're showing you that it's a parabola. The first biggest term tells you what kind of graph it is. And then they're asking you this. And what does this mean? Well, if you'll remember, f of 2 means you're taking 2 and you're putting it everywhere you see the x in the formula. So you're solving the formula. So 2 squared is 4, plus 3 times 2, which is 6, is 10, minus 4 is 6. So f of 2, the result is 6. F of x is the same as saying y is equal to, but f of x gives it much more flexibility. F of minus 1, the same thing. I'll get to that in a second. But my point is, you want to read through your chapter. Even how I'm doing it is fine. And if you spot something you need to realize, you go, okay. And this is teaching you how to do translate a spatial problem into a formula, which you'll need. And you got to remember that at high school, you might say, what is the point in this? High school is about preparing you for problem solving. The point of this is in science, you're going to be given a whole bunch of unknown variables, and you're going to have to come up with the tools and methods to solve those unknown methods. Now, you might end up with a job that's very simple, the same method over and over again, but the cutting edge research, they're coming up with their own tools, and it's built on the last tools, which are built on the last tools, and built on the last tools. So as the old joke goes, why you're learning why the mitochondria is the power center of the cell, it's because if you don't know that, you'll never become a microbiologist. So before you jump off the bridge, realize that it's all about taking tiny steps, and they're not so hard. So they're going to run you through here how to determine if something is a function. And they're using the one-to-one method, but they're also using the vertical line test. And then they're asking you to remember what asymptotes are and how to find a horizontal asymptote. We're going to get into all that. Then once you've realized, and then you're also going to have wheel puzzles. So you might as well look through this because it's going to be in your year. And realize that everything you learn, it's not like you can skip the first 3 chapters and then jump to chapter 4. It's not like history. Chapter 4 needs chapter 3. Chapter 3 needs chapter 2. Chapter 2 needs chapter 1. But what's brilliant is at the end of the chapter, if you have a feeling you already know the chapter, this is what would go into your notes. A summary of what this chapter is all about. And it's fantastic. You can just take a picture of this and make electronic notes if you want. But it gives you a great summary of everything that was learned. So they're giving you a graphical example, numerical example of a function and how to figure out its function, an algebraic example, which just means a formula, and what you need to know. Function notation. You need to know the vertical line test. You need to know how domain and range of a function depend on the type of the function. And you need to know domain and range of a function that models a particular situation that needs to be restricted. So, and they give you an visual example of what is a function, what's not. Then my recommendation to you is jump straight to the questions. Check your understanding means, did you understand this chapter? If you can't do it, go back and read the relevant spot. But my point in this video series is to do these questions. I will review basically the what you need to know concepts, but really if you don't need to know that, watch my other videos or go back and refresh your other courses. So let's go back into check your understanding, okay? Here we go. Skills and concepts you will need. So I do it this way. I take an image of the text and I throw it up into here, and then I just say, okay, what are we studying? Okay. Here we go. So I'm going to grab the first 3 and I'm going to make a new one. Here we go. The first one, as I said, they're asking you to remember what functions are and how to do functions. So when I see f of 2, what I'm doing is I'm taking that 2, and everywhere I see it in the equation up here, I'll make it a bit wider, everywhere I see x in the equation up above, I'm putting in a 2. Putting in a 2 there, and putting in a 2 there. So, what's 2 squared? It's 4. And then it was plus. What's plus 3 times 2? 6. And then minus 4. So what is that? 4 plus 6 minus 4 is 6, which means f of 2 is equal to 6. And that's like saying, what is y when x is equal to 2? It's 6. So if you're going to graph this, you would then take your Cartesian graph and you would find your 2 value on your x chart, 2, and then you would find your 6 value on your y chart. Sorry about the drawing. And it's right there. And as we continue to draw this, this thing's either going to go up like this or it's on the way up, but it's a parabola for sure. And one of the spots is going to be 2, 6. And then they just ask you to continue on with other things. And it's the same method. So what do I do for the next one? When it's asking me my f of minus 1, it's the same thing. They're asking you to take minus 1, and everywhere you see x, put a minus 1. So minus 1 squared plus 3 times minus 1, minus 4. So don't forget your rules. What's minus 1 squared? Anything squared becomes positive, so it's plus 1. plus 3 times minus 1 becomes minus 3. And then minus 4 is all alone. So what's plus 1, minus 3, minus 4? Here's where you have to remember your line rules, and 0 is here. Anything to the right is positive, anything to the left is negative. So if you want to look, we're starting at plus 1 right there, and we're going 3 to the left, minus 3. We end up at minus 2. And then we're going to subtract 4 now. So we're going to go 4 to the left, minus 6. So just lay down all the numbers here and you'll see how I did that. Another way to think of this is when you're subtracting two negative numbers, like minus 2, minus 4, you're going to get an answer that's the same as adding two positive numbers, except that there's going to be a minus in front of it. What's plus 2 plus 4? 6. What's minus 2 minus 4? Minus 6. So when you see a minus number minus a number, it's the same as adding them, but there's going to be a minus in front of them. You can try that trick with anything, like minus 20 minus 4 is the same as 20 plus 4. 20 plus 4 is 24. So minus 20 minus 4 is minus 24. When you're subtracting two negative numbers, it's actually quite easy. Where people get confused is when suddenly you add a plus in there. All right, so the answer to f of minus 1 plus 1 minus 3 minus 4 was minus 6. So my f of minus 1 equals minus 6, which means when x is minus 1, y is minus 6. So if I was going to put that into the same drawing, you'll discover a pattern. There's a 2, 6 up here, and there's a minus 1, minus 6 down here. We still don't know the vertex. Notice this fraction. This fraction's challenging you a bit, but it's the same rule. It's the same rule. We're going to take minus 1/4 and we're going to put it into this equation. So let's do that. What's 1/4 squared? Well, you're going to learn that a fraction times itself is the numerator times itself times the denominator times itself. What's 3 times 1/4? Well, in this case, the 3 is over 1, so the numerator multiplies itself and the denominator multiplies itself. So you get 3 times 1/4 is 3/4. And then finally, minus 4. Well, the problem is you might say to yourself, well, I can't come up with a numerical digit there. Well, there's two ways to approach it. You can make them have all the same common denominator, or you can just work in whole numbers. Let's convert it all to a common denominator. The 16 is the largest one. How do I turn this 4 into 16? I have to multiply it by 4, but it means I have to multiply the top by 4 as well so that I don't change the number. So I end up with 12 over 16. Okay, 12 over 16. How do I convert a minus 4 to something over 16? I have to multiply the top, because minus 4 is over 1 essentially. I have to multiply the top and the bottom by 16. So minus 4 times plus 16 is minus 64. So I get minus 64 over 16. How do you add all that up? Well, what's 1/16? Sorry, this should be a 16 here, sorry. What's 1/16 plus 12/16? That's 13/16. So these two add up to 13/16. And then what is minus 64 over 16? Well, let's just focus on the top because it's going to end up over 16 no matter what. You can look at it as plus 13 minus 64 or minus 64 plus 13. So if I'm at minus 64 on my number line and I move to the right 13, I'm going to end up at minus 51. I'll let you figure out how to do that. So the answer finally is minus 51 over 16. If I was going to convert that to a number, and by the way, your teacher's not going to like irrational numbers, which is like 2.5369472. He would prefer it in whole numbers. Well, 16 goes into 51 3 times, so I get minus 3. And what's minus 3 times 16? Minus 48. How much is left over? 3 over 16. This can't be simplified, so the whole number is minus 3 3/16. I could also turn it into a decimal by taking 51 negative divided by 16. Minus 3.1875. Minus 3.1875. Which means when x is 1/4, y is minus 3.1875. So on a graph, it would be just over here on the right side of the x line, and then down here, be somewhere around there. So we can see we're looking at something that goes way down here, up here. So that's where Desmos would be good, just to draw this, right? To get an idea. Finally, you're going to be faced with something like this. What? How can I deal with a number? Well, try to remember that the whole point of functions is to study unknowns. And sometimes you can plug an unknown into an unknown. So it's the same rule. This is like your x. So everywhere I see the x, that's what I'm going to put. So it's 3 times that now. And then finally minus 4. I'll just do it like this. There we go. And you'd resolve it. Well, you're going to discover, if you remember, a plus 1 squared is the same as a plus 1 times a plus 1. Anything squared is itself times itself. And you're going to end up with a squared plus 2a plus 1. Okay, so that goes there. Then you're going to remember your distribution rules, 3a plus 3, which just means whatever's in the bracket must be multiplied by whatever's out in front, and then minus 4. So now you've got this whole mess here. So again, the secret is you're going to group your common terms. I'm going to circle my common terms. Plus 2a, plus 3a, or sorry, square, I should have said. And I'm going to put a green square around my common number terms. Okay, very quickly, what's plus 1 plus 3 minus 4? It's 0. So those will just cancel out. What's 2a plus 3a? 5a. So the final answer is a squared plus 5a, which means when x is equal to a plus 1, y is equal to a squared plus 5a. Not really an answer, not really graphable, but that's the answer. That's what's called as far as we can take it. Factoring, it's going to want you to remember how to factor, and I hope you remember how to factor because factoring is incredibly important. And you're going to be using it even in university, especially if you go into higher mathematics. And you're going to discover, wait a minute, what's going on? You know, what are they asking? Let's start with an easier one, numbers. So if you remember, this is a complicated factor, and it's complicated because there's a 5 in front. Your first step is to see if you can get rid of any of these numbers by factoring out in front. You can't. 16 and 3 and 5 have nothing in common. Your next step is to say, what's 5 times 3? It's 15. Okay, what's the middle term? It's minus 16. What number times itself can create a positive 15, but added together creates a negative? Well, that means we're dealing with two negative numbers. And the only thing that works here is negative 15 times negative 1. When I multiply these two, I get plus 15, and when I add them, I get minus 16. Now, I use what's called a slip and slide, but you should use your grouping until you get used to it. Grouping says this. I'm going to put the number, I'm going to split this minus 16 into these two terms. So I'm going to get 5x squared minus 15x minus 1x, which is the same as minus 16, and then plus 3. And then I'm going to factor two things at a time. I'm going to just get rid of some of my mess. I know I'm pretty messy. Okay, I'm going to get rid of some of my mess. So the secret to factoring this now is I'm going to factor this independently, and I'm going to factor this independently. And that little chicken scratch up there has nothing to do with it. Okay, what's common in here and here? 15x and 5x squared. Well, I can take a 5 out, and I can take 1x out, and I'm left with x. When I divide this by 5x, what happens? Well, 5 disappears, and I'm left with 1x. And you're going to have to remember your power rules, exponent rules. So I'm left with x. And just to test it out, if I multiply this out, I indeed get 5x squared. What about this one? When I divide this one by 5x, I get minus 3, because it's a minus 15, and the x's cancel out. So I get x minus 3. Hint, hint, that's probably what I'm going to end up with over here. You might say, well, you don't have to factor out anything because that's a 1x, but no, it's a minus 1x. So I'm going to factor out minus 1 because I always want my factors to have just one x and one positive x to boot. So when I divide this by minus 1, I get positive x. When I divide plus 3 by minus 1, I get minus 3. Lo and behold, this term is multiplying that, and this term is multiplying that, which means I can factor out again x minus 3. I can factor out x minus 3 from the whole thing. What happens if I divide this whole thing by the way, that's what all factoring out is you're dividing out something. Well, if I factor out, I'm just left with the 5x, right? So I'm going to factor out x minus 3 from this first term, and I'm left with 5x. And when I divide this whole second term, factor out this x minus 3, I'm left with minus 1. And look at that, the other two terms were right there, and always will be. And there you go, it's factored by grouping. If ever you're in doubt that you got the right factors, distribute this again, and you'll discover that you indeed got the right factors. And that's factored by grouping. I like the slip and slide method. Look it up on YouTube, and you'll discover it. Let's go to something more complicated. Well, you have to use your brain here and say, it's the same thing, except ask yourself, well, what's in front there? This might be tough to see. Ask yourself, if it was x plus 1 squared, what would I end up with? Well, I'd end up with x squared plus 2x plus 1. Notice I ended up with the square of this one here, the square of that one here, and the middle was 2 times this term times that term. Well, this is a perfect square. That's called a perfect square. And if you look carefully here, and you might say, how did you come up with this? That's the factor of that. And I spotted it because it's a perfect square, and because there's a single version of this one here, and a single version of this one here, and these two here are perfect squares. The square root of that is x, the square root of that is y. If you try to figure it out algebraically, like the way we're doing it, you'd have to say, what two factors will create y squared and 2x? Does that work? 1 times the 1 is y squared. I think it's 2y actually, yeah, and 2y. Because this x and this x squared are the same thing as we were doing before. We don't involve them in our factoring. Well, it becomes quite clearly that 1y and 1y, when I multiply them, becomes y squared, and when I add them, becomes 2y. Which means, since those are the same factors, and this does not have a complicated factor in front, I can just factor it like that. Since it's the same factor, it just squares itself. Complicated, isn't it? Now, what are they asking here? Well, they're asking you to remember the difference of two squares, but they're being kind of jerks about it because they're giving you a complicated one. If I simply said x squared minus 64, you might immediately say, that has a square root of x, and that has a square root of 8, just the number, not the minus. And you say that's a difference of two squares. It's x plus 8 and x minus 8. And you'd say, I remember that because the middle terms will always disappear. And remember that. The middle terms will always disappear. X squared minus 8x plus 8x, so the middle term disappears, minus 64. So that's why there's no middle term here. So a difference of two squares, the middle term always disappears. Well, the secret here is to realize, that's got a square root as well. The square root of that is x plus y. So instead of thinking, let's look at our x squared again. Okay, and we're going to do the same thing we did in other things. It's x plus 8 and x minus 8. But this time we're going to say, instead of x squared, I'm going to use what they gave me. I'm going to say, instead of x here, I'm going to take, which was the square root of x squared, I'm going to replace this with the square root of what that is, which is x plus y. So really, in here, I'm dealing with the square root again. And in the second one, I'm also dealing with the square root. These are all things from last year, and you have to get comfortable with spotting it. So it just becomes x plus y plus 8 and x plus y, sorry about the drawing, minus 8. And those are the two factors of that difference of two squares up there. complicated, isn't it? Then they want you to learn in the D example, they want you to remember grouping. They want you to remember grouping. So there's always a purpose to these things, like why are they making me do this? If you look at this, what does the first one have in common? It has X in common. What do the second two have in common? They have Y in common. What don't we like? We don't like a minus. So in the first one, the only thing I can factor out is an X, and I'm left with A plus B. In the second one, I don't like having a negative in front, so I can factor out a minus Y from both, and I'm left with A, positive B. Notice I have two factors multiplying, two terms that are the same multiplying these terms, which means I can factor out A plus B from both of them. And I'm left with X minus Y. And there we go. I've managed to factor this thing by finding the commonalities in two terms. That's called factored by grouping. And that's why they want you to do it. Number 3, they want you to revisit transformations. Nothing's better than using Desmos for your transformations. Just remember that Y transformations are super easy to figure out. And X transformations kind of do the opposite. And that's true for all functions. So it's the same rule over and over again. So here they're giving you the parent function. So we're dealing with the standard parabola. And then here they're saying the new one, the new function, is going to be the f function I gave you here, but you can see I'm affecting the x. Clearly that affects the x. And anything outside the brackets, away from the x, is going to be affecting the y. So if it was another y thing out here, you'd have a 3 in front of the f. That would be a y thing. If it was affecting the x, you'd have a 3 inside the f. You might say that plus 2 looks like it's inside the f, but if it was, it would be over here inside the bracket. Okay, so that means I have an x transformation and a y transformation. Always let's look at your y transformation. So all my y values are going to go up by 2. So whatever y values I have for my parent function, I can just add 2 to them, and I'm going to get my new y functions for this transformation. But what happens to my x transformations? You might be tempted to say they all get subtracted by 3, but no, x does the opposite. All my x transformations get added to 3. So whatever x values I have in this parent function, I add 3 and add 2 to the y values, and I'll be able to plot my new one. So essentially this entire parabola moved to the right by 3 and up by 2. And if you know the values of this parent, which is the point of studying the parents, you can now graph this transformation. They want you to sketch it. What I would suggest to you instead is learn your Desmos. So here's the parent, and I'm going to make the transformations right here. And there you go. You can even ask it to give me a table of values, and you can verify that those transformations did indeed occur. What would be better is if I actually added 3 to each of these x values to show what happened to them. So what I did is I took the x values from up above and I added 3 to each of them to get these. I didn't do that one correctly. It should be positive 1. And then you'll notice the y values automatically got added 2 to them. See all the y values up here? They're now 2 more down below. So you see, by taking the exact x values from up here and adding 2 to them, which is one of the transformations, 3 to them rather, I automatically got my y transformations because it calculates it for me right there. But I can also click on them and you can see the course there. 0, 0 went up to 3, 2. So it added 3 to the x and 2 to the y. It's where Desmos is fantastic because you can see exactly how these transformations work. Notice the blue curve is indeed 3 to the right and 2 up of the red curve. That's the only transformation that happened. Why struggle when you have this tool? Use this tool to verify your answers, not to cheat, but to verify that you're on the right track. Okay, let's look at B. First of all, if you haven't done it, take Desmos and revisit all your parent functions. X squared, square root of x, absolute value of x. Those parent functions will come again in calculus, and you need to know them. So what's the parent function here? Well, that x is an exponent we're talking, and this 2 is bigger than 1. So we're talking about a growth curve. Growth curves all go through 0, 1, and 1, the base, 1, 2 in this case. And they all look like this. They never approach y, and they go through the y-axis exactly at 0, 1. That's the parent. What's happened to the transformation? Well, all the y values have gone up by 2 again, and all the x values have gone plus by 1. So right away I could take these two values and add 1 to the x's and add 2 to the y. So this new coordinate would become 1, 3. And this coordinate here would become 2, 4. And right there, I have my new coordinates, and I could sort of sketch the same thing. I also want to point out that because this whole graph went up by 2, and normally there's a horizontal asymptote at the x-axis, that because this whole graph went up by 2, the new horizontal asymptote will be at y is equal to 2. So essentially the horizontal asymptote went up by 2 as well. The entire graph went up by 2. To test this out again, Desmos, fantastic tool. So here we've got it's 2 to the power of x. Okay, it's going to come up with some basic values. G of x is equal to x minus 1 plus 2. I'm going to take some of the same values I had before, and actually let's just get rid of these ones and work with those ones. And so I'm going to add 1 to that, 1 to that, and 1 to that. So just sort of ignore the other ones. There we go. So you'll see that indeed the y values had 2 added to them. And this is the new graph. I also want to point out the new horizontal asymptote is indeed at, and I can change colors by holding this down, is indeed, let's make it black, is indeed there. And you might say, oh, that touches the horizontal asymptote. No, it doesn't. Not when you zoom in, it doesn't. Never reaches the horizontal asymptote. If you can't remember why, go back to your basics and study this parent graph. Again, as I said, you should be studying your parent graphs religiously to get a good idea of what's going on. Okay, so study this red graph, understand some key points on it, and even on this side of it, because your transformations are going to happen again and again. What about this one? This is a sine curve. Okay, so they're making you practice the same sort of concepts, but they're making you revisit the curves again, the functions again. Okay, I'll just move that one there. Very important to study your parent graph. So if you remember the sine curve, there's 5 key points you should remember on the sine. 0, 0 goes up, 90 degrees, 1, and this year you're going to be working in pi radians, so we're going to have to get back to learning pi radians. 180, 0, 270, minus 1, and finally 360, 0. Those are the 5 major points that you should know in a sine curve. What happens to the sine curve? Oops, that minus is tricky. So notice this minus 2 is outside of the g, so that means it's a y values. All my y values will be multiplied by minus 2. What will happen to all my x values? You'd be tempted to say all my x values will be multiplied by 0.5, but actually my x values will be multiplied by 1 over 0.5, which is 2. So all my x values will be multiplied by 2. All my y values will be multiplied by negative 2. So looking at these right away, this first one won't change at all. By the way, what does this do? This creates a reflection in the x-axis and stretches it by 2, which means it's going to go deeper and higher. And what does this 2 do? Normally you'd think of this as a compression because it's less than 1, but it's actually a stretch by 2, which means all my y values will, redrawing that, will be twice as long. And I got the drawing wrong, but that's the basic idea. And you just take these values and you multiply them by minus 2. So it's going to be minus 180 and positive 2, comma 2. Yeah, so it's actually going to be minus 180 is going to be on this side of the graph. It's going to be way up there. And this one is going to be minus 360, comma 0. So it's going to be, it's way over there. So that's using the exact points. So again, it's always good to use Desmos. And we'll get rid of that. And it helps if you convert things. See, this one's doing it in radians already. And then this next one, remember, we're going to put a minus 2 in front and a 0.5 in front of x, just to give you an idea of what it looks like. There we go. The blue one is the transformation. See how it's reflected downwards? See how it's twice as long? So, yeah, we could have done it like this too. But the translated points we were working on are actually way over here. In any case, the blue is the transformed version of the red. Fantastic tool. Get used to your Desmos. Finally, this one's looking at the square root function. You're going to have to remember that the square root function has some limitations. Okay, and the standard one's like this. It goes up. Oop, it goes up like that. Notice we haven't even gotten to the questions yet. Okay, it's got a restriction on the domain and the range. All the x values are positive, or rather above or equal to 0, and all the y values are above or equal to 0. What does this transformation do? It's multiplying all our y values by negative 2, and it's multiplying all our x values not by 2, but by positive 1/2, the reciprocal of what's in front, which means we have a compression on the x and a reflected and negative stretch down there, which means our graph would be reflected like this. Let's see if I can do. I'll do it in purple. So all my y values are going to go deeper, and it's going to be fatter because it's compressed. Some key values here on the green graph: 0, 0, 1, 1, 4, 2, and 9, 3. So if I multiply all those y values by minus 2, I get minus 2. And if I multiply all those x values by half, so I'm mixing up my y values. That's why I screwed up the other one. Minus 2. And all my x values by half, so I get a half, comma, minus 2. So it's down there. And then this 4, 2 becomes 2 when I multiply by half, comma, minus 4. So it goes way over there, and etc. Now you can do this the same way. Sorry, I screwed up the transformations of the sine curve. 2 and 2 and negative 2. There we go. And you can see this when I put in my x values here, and then for this one, yeah, notice it can't do minus 2 and minus 1. Doesn't exist. And I like to use 4 and 9 because they have square roots. And then if I take the graph of this one and then just simply multiply the x values up above by 2 or negative 2, by half and negative 2, I get 0, 0 for that one. And this one I'm going to get 0.5. There's the minus 2. This next one I'm going to get 2, and this next one I'm going to get 4.5. And then all the y values will fall in line. These are the 3 exact transformed translated points of these 3 points. These 3 points, the x values have been multiplied by half, and the y values have been multiplied by minus 2. Did I get that one wrong? 4.5, yeah. Oh, there it is, down there. These 2 points correlate. 9, 3 becomes 4.5 minus 6. Do the calculations if you're not sure, but it makes life a lot easier. And sure enough, the graph is indeed reflected in the x-axis, stretched vertically by 2, and compressed by a half. Those are all useful things to revisit. Super useful things to revisit. State the domain and range. So again, they want you to practice stuff from grade 11 functions, right? Okay, here we go. Domain is dictated on the x. Notice that this has a limitation. It doesn't go below minus 2x, but it includes minus 2x. So it's minus 2 is smaller or equal to x, is smaller or equal to positive 2. There is a function notation for that, which would be which I think it's rounded brackets, minus 2, comma 2, rounded brackets. I think the rounded brackets means it includes, but I'll have to revisit the function notation. That essentially tells me the domain. And then, so that's A. And then the domain is strictly dictated by the y, but notice I believe it includes 0. So in this case, y is bigger, 0 is smaller or equal to y, and smaller or equal to 2. And in function notation, I believe that's a roundy bracket, 0, comma 2, roundy bracket. The roundy bracket means we're including these numbers. Again, revisit the function notation. It might be a roundy bracket like this, but could be, instead of that squiggly, that it's a roundy bracket like this. And a square bracket means it's not included, but I'll have to revisit. I believe it's like that is included, and that it means not included. Anyway, that's of this circle one. What about this one? Well, to figure out, that's a parabola. You just have to revisit your knowledge of parabola. For all parabolas, XER, which means x goes on forever and is all real numbers. But y is dictated by its vertex. To find its vertex, you would either need to graph it or complete the square. And that's probably what they want you to do. So very quickly, there's videos out there that will help you complete the square. But I believe this is it. Which means the vertex is 3, comma, positive 3, comma, negative 19. And since this is an upward facing vertex, that means that minus 19 is the bottom, the minimum. And that means my y values are bigger or equal to minus 19. To make sure, we'll just plug that into Desmos, x squared minus 6x minus 10. And sure enough, there's the vertex, 3, comma, minus 19. Again, Google in YouTube search, completing the square. There's guys who are very good at explaining it much faster than me, but you're essentially focusing on this part of it. Then you create some numbers you don't want. You have to subtract them. Okay. This one here, you have to go back to your parent function and understand your parent function. That's the typical reciprocal function. That means it looks like this. And over here in the red, the quadrant 1, it looks like that. And quadrant 2, it looks like that. Or quadrant 3, rather. Looks like that. It has two asymptotes. X cannot be equal to 0. And y cannot be equal to 0. And you should learn it. Which means that YER is the domain, but y cannot be equal to 0, which means all values of y are possible except 0, and x is ER except that x cannot be equal to 0. All possible values of x except 0. And that's domain and range for that parent function. For sine curves, you have to understand what the 3 does. The 3 is the only thing transforming the sine curve, and it is stretching. It is a y influence, which means all the y values are stretched. Well, you have to know that a normal sine curve goes only as high as 1, positive 1, and only as low as minus 1. Now, since the sine curve can go on forever, XER. And since this one is not affected, the x's aren't affected, it's XER still. But the range is dictated by the max and the min height. When you multiply by 3, the highest it goes now is plus 3, and the lowest it goes is minus 3. And since there's no transformation here, the axis is still right here at the x-axis, which means minus 3 is smaller or equal to y, is smaller or equal to positive 3, and y is any real number. So that's the limitation, which I believe is written like this in function notation. And again, forgive me if I'm using the wrong curvy brackets. This requires your knowledge of the parent curve of the sine curve. What about this? This is an exponential function. And it has not been altered except the base is 10. Which means the standard two spots that I know will exist is 0, 1. And that's because when x is 0 up here, any exponent to the 0 is 1. And the other one will be 1, the base. 10 to the power of 1 is 10. Which means we have a standard growth curve like this. Nothing else has been altered. Which means XER, just like a normal growth curve, but the y, it never touches the x-axis, so y is bigger, not equal to 0. There you go. That helps know your parent curves. This, they're asking you to review what functions are. Will this pass the vertical line test? No. Therefore, it is not a function. What kind of function is this? Right away I can see it's a parabola that has some transformations, but a parabola. And parabolas are indeed functions. Oh, here they've done a plus minus sign for the square root, which means not only do I have this part of it up here, I also have this part of it down here, and it will not pass the vertical line function, vertical line test, so it does not. Here I simply have a growth curve that's been adjusted down by 4. Its base is 2, but all growth curves, as long as they're still growth curves, are functions. So yes, 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 no, no. And here we just have a cos curve that has been translated 30 degrees to the right, compressed by half and moved up by 1, but cos curves, even transformed, are still functions. So yes, 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 no, no. Here they're just asking you to review your knowledge of how to work backwards from a graph. I'll just get rid of that. So we're dealing with a cubic. Again, it helps for you to remember what a cubic starts with. When there's all cubics start in quadrant 3 and end in quadrant 1, which means it starts here, squiggles through there, and goes up. And they are XER. But if 2n is a point on the graph, determine the value of n. Well, that just means if 2 is x, 2 cubed is 8. So 8. So that means there's a point 2, 8 here. Now they're asking you to work backwards. If we don't know the x value, but we know the y value is 20, determine m correct to 2 decimal places right away. That's a hint that it's not going to be a simple number. Well, let's just plug into the equation again. But we don't know x this time. Normally we'd put x there. So m to the third is going to equal what? But we do know y this time. They've given us y, 20. Well, when we take, how do we get rid of this third? We cube root this side. If we cube root this side, we've got to cube root that side, which means m is equal to the cube root of 20. When I take my calculator and punch in 20, and then I've got to go to second function, I think. Yeah. And there's cube root right there. I get 2.144, and they want it to 2 decimals, so it's 2.71. X is 2.71 when y is 20. There's the answer. Great. And then finally, list 3 different ways. Function can be described in or defined in many ways. List these different ways and explain how each can be used to determine whether a function is a relation or a function. Well, a relation is when it's not a one-to-one ratio, when it doesn't pass the vertical line test. The whole point of a function, as we've seen from the virus, is to be able to predict a y based on the x. Well, you can't predict a y if there's 2 possible y's. So that's where a relation's useless for our prediction models, and functions are very good. They predict the weather with functions. They predict the pandemic virus spread with functions. They're called models. And they're very complicated, but once you know all the factors, you can predict the future. Anyway, I could go into this. That's in your book. I'm here to solve numbers. Boom, we finally got through all those reviews. You can see how long it would take if you don't know them. But it's very important to always go back and, solve the quadratic function. So, okay. Skills and concept. Oh, did I accidentally solve? Was I accidentally solving the stuff instead of going over the skills and concepts? I think I was. No, I wasn't. What the hell was I solving? Did I just waste everybody's time? Oh, no, I didn't. There it is. Yeah, there you go. I was just in the wrong textbook. Okay, so 1.1. Now they ask you to go through and actually solve some stuff. Yeah, they're making you practice functions again. It's actually some of the similar stuff. State the domain and range of each relationship. Okay, well, domain, it's going on forever. Range, it's obviously dictated by the y values here and here, and it includes them. So minus 4 is smaller or equal to y is smaller or equal to minus 2, and that's the range of that one. This one is a finite graph that I'm going to assume ends right there, which means its domain also is finite. Its domain starts here and ends here, and those x values are minus 1 is smaller, and I'm going to assume it's equal, included, and smaller or equal to 7. That's the x value right here. The y values, the range, is limited by this. And if it went on forever, you'd see a little arrow here. So clearly it stops right here, and I'm going to assume it includes it. So that's the range here and the range here. And that's minus 3 all the way up to plus 1. So minus 3 is smaller or equal to y is smaller or equal to 1. Okay, what about C? Well, notice for these are easy. The domains are always just the numbers, and this function this is not a function because of this right there. And does it say then determine whether the relationship is function? Yes, because it passes the vertical line test. No, because these two x values lead to different y's. But the domain is 1, 2, 3, 4, simply all the x values, and the range is 4, 9, 7, minus 5, and 11, and then I would rearrange them in numerical order. So it's minus 5, 4, 7, 9, and 11. And is it a function? No. This is a line, this next one. I'm going to kind of delete stuff as we solve it. And all lines are functions. And all lines, unless they're horizontal or vertical lines, are not functions actually, but that's not a vertical line. But all lines go on forever. So x, er, and y, er. And then here we can see that each x value is unique and leads to unique y. It doesn't matter if the y's repeat, only if the same x's lead to different y's. So that means the domains here are x values, minus 4, minus 3, 1, and 2. and the range are 0, 1, 2, and 3. And you'd write those in little, I think, squirrely brackets to say this is it. That's all. And then this is a downward facing parabola, which means XER. All parabolas are XER. And the domain, or the range rather, depends on the vertex. And when there's nothing adjusting the X and being added here, the vertex is 0, 0. This is just a stretched and reflected parabola, -5. So that means 0, 0, which means y is smaller because it's downward facing because of this negative number. Y is smaller or equal to 0, which means the range values of this parabola only exist below 0. There you go. Okay, let's go on to number 2. And if ever I'm speaking too quickly, just stop and rewind. But I also want you to pause after I solve one and see if you can solve the next one, and then hit play to see if you got it right. And keep doing that until you keep getting it right. Notice the first two questions are always going to be super easy. State the domain and range of each relation, then just determine the relation is a function, justify your answer. This is, I'm going to go backwards and determine if it's a function. This is a parabola. It is a function. This is a growth curve that's reflected in the y-axis, so it's still a function. This is a circle, so it's not a function. This is how all circles look. This is a rational function, therefore a function. This is a cos curve that's been adjusted up by 1, therefore a function. This is a sine curve that's been stretched by 2, therefore a function. What's the domain of a parabola? Always XER. What's the range of a parabola? It's dictated by the vertex. The vertex here is -1, comma, -3, which means, since this is facing down because of this minus, that the range is smaller or equal to -3. Put it in a Desmos if you're not sure. What about this one? Okay, normally this is a rational function where x is ER and y is ER. I'm talking about this one here, by the way. And except that x can't be 0 and y can't be 0. Except this x plus 3 means all my y values have been moved 3 to the left, which means the vertical asymptote has been moved 3 to the left. So now x is no longer can't be 0. X can't be -3. So that means XER, but x cannot be -3. YER, y cannot be -0. If in doubt, put that into your Desmos. And put in a x is equal to -3 asymptote, and yeah, there you go. You'll discover that the new asymptote is moved 3 to the left. Desmos is great for not having to phone somebody. Okay, what's going on with this one? That's still a growth curve. All that -1 in front of the x does is, instead of a growth curve with a base of 2, instead of a growth curve like this, in which it goes like this, sorry, it hugs the x-axis and then goes up, and it would have 0, 1 here, and 1, the base here. This minus means I'm reflecting everything in the y-axis. So it's going to go this way. It's going to go through that 1, 1. But now over here, all my x values are multiplied by -1. So I get -1, 2 is my new value over here. Didn't change my domain. My domain is still XER. And it didn't change my range. My range is still y bigger than 0. Because it never touches the growth curves never touch the x-axis, and that's their base. So that didn't actually change anything. Had they lowered the whole thing, it would have, or raised the whole thing. If we'd seen a +4 over here, or a -4, it would have changed my range, but not my domain. Okay, what about this one? Well, we just have a cos curve that's been raised by 1. So again, you just have to know that your cos curves normally only go as high as +1. Oh, so their x is XER. XER. So domain goes on forever. But their maximum is usually +1 and their minimum is usually -1. However, I've raised this whole graph by 2, which means this max, sorry, by 1, which means this max has now gone up by +1 to +2, and this -1 +1 has hit the x-axis. So it's going to have a new axis here. And now you can see my range falls between those two values. So 0 is smaller or equal to y, smaller or equal to +2. If in doubt, put this into your Desmos and you'll see what has happened. It's a cos curve that's just been raised. And yes, it's still a function. This is a circle. It goes through 0, 0. Its radius is 3. The radius is always the square root of that number. So 3. Which means if I were to draw it, it would go over here to 3, 0, and over here to -3, 0, and up here to 0, 3, and down here to 0, -3, and then I would put a circle around there. And you can see the domain is -3 is smaller or equal to x, smaller or equal to 3, and the range is the same. Just got to know what shape that is and throw it into Desmos. Again, this is a sine curve that's been stretched by 2. Nothing else has changed. And as I said for cos curve, the sine curve's max is 1 and the min is -1. But this multiplies all my y values by 2, which means my max goes up to +2 and down to -2, which means my range, it goes from -2 all the way up to +2. But my domain is still XER, goes on forever. So all that is a stretch sine curve. Stretch changes the amplitude and nothing else. And therefore the range. Okay, practicing. Oh, that's pretty basic stuff coming up. I don't even know if you need help on this one. So they're just asking you to work with both visual, 2 different types of numerical functions. Determine whether each is a relation function showcase its domain and range. Okay, this is still a function. You can share the same y with 2 different x's. You just can't have the same x's. So that's a function. Here's the domain, 1, 3, 5, and 7. Here's the range, 2, 4, and 6. This is not a function because we have, oh yeah, no, it's still a function. My bad. My bad. You can have the same y value for 2 different x values. My bad. And here's the domain, and here's the range, 2 and 4. So it's its function. This you can't have. See, this x leads to 2 different y's, 0 and 1. So it is not a function. However, this is the domain, 1, 10, and 100, and this is the range, 0, 1, 2, and 3. Do we have any repeating x's here? No, we don't. Therefore, it is a function. The domains are all the x values in numerical order, so 0, 1, 2, and 5. And the range is all the y values in numerical order, -1, 3, and 6. You don't have to write the 3 twice. This is not a function because that 2 leads to 5 and to 7. So it is not a function. And the domain is, in numerical order, 2, 6, and 8. And the range is 1, 3, 5, and 7. So it's a relation, not a function. And these all have unique x's, so they're good. So it's a function, so it's 1, 2, 3, 4 for the domain, and 1, 2, 3, 4 for the range. Pretty straightforward. I don't think that was like grade 11 work. So you'd use the vertical line test for this one. Yes, it is a function. Vertical line test for this one says no, it isn't a function. This one looks tricky, but really it's just a parabola. And I might as well walk you through what you do in situations like this. You always try to just get the y on all alone on one side. Okay? So if I get it all alone on one side, I'm left with 2y. You've got to use your algebra. X squared minus 1. And then I divide both sides by 2. And I get x squared, a half in front of the x squared, minus 1/2. So all that is, written like this, is a parabola that's been compressed by half and then lowered by half. So it's still a parabola. And all parabolas are functions. So if they're asking me if it's a function, the answer is yes. Oh, they want domain and range. Okay. So going back to this one, the domain for all parabolas goes on forever. The domain is going to be y is bigger or equal to 2. For this one, the domain is limited. X is bigger or equal to 2. And the range goes on forever. For this one, all parabolas, it's going to be limited by its vertex. So the domain goes on forever, but its vertex is 0, comma, minus a half. And since it's upward facing, it's positive here. That means y is bigger or equal to a negative a half. And if you're in doubt, put either one into the equation. This should look the same as that. And you'll see a parabola that has a vertex at 0, comma, minus a half. What's going on with this one? How do I solve this one? Well, again, you got to get y all alone on the right. Y squared is equal to x. The only way to get y all alone is to square root both sides. So we're left with a tricky looking function. Y is equal to square root of x. So this is just another way of writing y is equal to square root of x, which we know is a function. And we also know x is bigger or equal to 0 and y is bigger or equal to 0 for the parent function, the square root function. This looks like it's 3 over x, I think, unless I copied it down wrong. Yeah, it's supposed to be 3 over x. It just got a weird extra squiggly. And we can see that's very similar to the 1 over x function with just a 3 multiplier, which just means it's stretched. That won't affect the domain and range. So it'll be x, er, except x cannot be 0. And as a result, y, er, but y cannot be 0. This is just 3 is just going to stretch it out. And you notice it looks confusing here, but I just factored out the 3 in front to see that it's a stretched rational function. What's this? This is a straight line, goes on forever. It's a function, and therefore x er and y er for all straight lines except for vertical ones. Vertical ones are not functions. Okay, I hate what's coming up here. I hate these word puzzles that don't really have a point. You'll see a few of them. I don't know if your teacher will ever emphasize them because they don't really have a practical purpose in science. I mean, very rarely is someone going to come up to you and say, hey, 5 people got more sick than the people from last week, but twice as sick from the people week before. Ugh. Okay, the input is 3 less than the output. The input is 3 less than the output. So y is equal to x minus 3. I don't know if these are all the same rule to the same function. I think each one has its own thing. The input is 3 less than the output. The input is 3 less. So if x was 1, y would be minus 2. Is the input 3 less than the output? No. So that means it's plus 3, which means if y is 0, or sorry, if x is 0, y is 3, and in that case the input is 3 less than the output. The output is 5 less than the input multiplied by 2. So what bugs me about this is, do they mean the whole thing multiplied by 2 or just the x? So that could mean 2x plus 5, or it could mean 2x plus 5, and that's why I don't like these word puzzles, is there's 2 ways to interpret it. Subtract 2 from the input, okay, then multiply by 3 to find the output. So I believe that's, notice line functions are the easiest functions to use for solving these things. And then the sum of the input and output is 5, okay, the sum of the input and output is 5. So that's just a line. I hate those. I don't really see them ever having a purpose in any of your future studies. Whereas models do. I mean, they use a lot of models today. This guy wants to build an additional closet in the corner of his bedroom. Because the closet will be in a corner, he only needs to build 2 walls. Okay, let's draw his room in red. And let's draw his closet in green. He only needs to make 1 wall here and 1 wall. I'm going to make the second wall in blue. No, in orange. Okay. The total length of the new walls, let's call this wall here y and this wall here x. The total length of the 2 new walls must be 12, so x plus y must be 12. X plus y is equal to 12 meters. Martin wants the length of the closet to be twice as long as the width. Okay, let's call x length. So he wants the x to be twice as long. He wants x to be equal to 2y. Shown in the diagram. Oh boy, let's see if there's a diagram. Oh, there we go. Okay, so they're labeling it like that, so I might as well use their labels. Okay, let's use their L and Y too. So L plus W is equal to 12. And L is equal to 2 times W. Use an L like that, which means you have 2 equations. Why is L equal to 2W? Because length is 2 times the width, twice as long as the width. Let the function f of L be the sum of the length and width. Find the equation for f of L. Okay. For f of L be the sum of the length and width, technically, you need the L all on one side. So you get L is equal to 12 minus W. And in proper notation, it would be minus W plus 12 because you have the missing variable first always, which means f of L. Oh, okay, yeah. Now, to solve this, that's a good point. I can't solve it like this with the width unknown because the idea is I have to find a function that fits in. Now, what can I replace L with that I already know down here? Right? I can replace L up here with 2W. And that's another interesting rule of math, is when you find an equivalent, you can replace it. So this would actually solve it. So notice I can get 3W is equal to 12. And W therefore is equal to 4. And then I can go back and say, okay, well, if W is 4, L is twice as long, 8. 8 plus 4 is indeed 12, and it is indeed twice as long. But if I'm going to write it the way they want me to do it, I'm going to say the function of L is equal to L plus W, because they asked me to do the sum of the length. Well, you'll see that I can't find f of, let's say, 4, because I can only plug the 4 into here, and I'd be missing a W. So I have to take that 2W is equal to L and isolate it. Say W is equal to 1 over 2L. And then I can replace my W out here with half of L. And then what's 1L plus half an L? 1L plus half an L, it's 1.5 L, which is also known as 3 over 2L, which means f of L is equal to 3 over 2L. So if I'm going to graph that, f of x, let's say, is equal to 3 over 2x, I'm going to get this interesting thing here. So I have all sorts of options, right? But only one of these options will ever add up to 12. Huh. Right? That doesn't add up to 12. That doesn't add up to 12. And we have to find a situation where one is twice as much as the other. And actually, did I do that right? So if L is equal to 2W, W is equal to L over 2. So, and then here I have 1L plus, instead of W, I have half an L, L over 2, which is 1.5 L. And the sum, oh, so when will this be 12? Okay. When is Y 12 is essentially what I'm looking for. Right there. Y is 12 when L is 8. So that means my total closet door will be 12, the function of the length plus the width, when the length is 8, which makes sense. And if the length is 8, the width would have to be 4. But you notice this equation doesn't involve width at all. It just involves L. Now let's see if it'll accept L. Yeah, it does, but I just have to put F of L in there, or get rid of it entirely and create a table from it. There. It's the same graph, F of L, but they've called it X1 here so the computer can understand it. But because I'm looking for a total X plus Y must equal 12, I would have to go all the way out here and say, when is my full length, or sorry, when is my total perimeter of the closet 12? So you'd have to keep adding, and of course we know from experience it's when L is 8. But width isn't even in there. This line is more about the total closet. So if I was going to obey those rules but change the total perimeter, I could have all these other options in the line, but the only one that works for when my total is 12 is right up there, when length is 8, which means width is half of the length, which width would be 4. Interesting way to see it. Find the desired length of width. I actually prefer it this way. Whenever you're missing two variables, you need two equations. We know that length plus width is equal to 12, and we also know that that length is equal to 2 times W. Well, I can replace this length here with what I found here. If length is equal to 2W, then I can replace this, which means 2W plus 1W is equal to 12, which means 3W is equal to 12. Divide both sides by 3, and I get W is equal to 4, which means, going back to here, if W is 4, then length plus 4 is equal to 12. That means length, subtract, is equal to 8. So when width is 4, length is 8, and it satisfies length plus width is equal to 12. That's the only situation where that'll work. So that means this is equal to 8, and this is equal to 4. However, what I did was indeed create a function based just on length plus width, replacing the W with a version of L, because you can't have F of L with a W in there. It just won't work. And it ended up creating a graph that showed me the total perimeter of the closet, and only up here does this dot suit it, because I'm trying to create a total perimeter of 12 in the closet. Thus it tells me the length 8, and W isn't even in there. I have to go back to figure out W. Hope that made sense. It sounds confusing, but it's just a useful tool. The following table gives Tina height above the ground. Okay, this is going to be a sine curve, because all wheels, they create either a cos curve or a sine curve. Cos curve and sine curves represent wheels or anything with a repeating function like tides, heat in the year, sunlight. So let's have a look and see what her maximum height is. 10, 10, 10, 10. Let's see her lowest height. Ground level, ground level, ground level. Happens pretty consistently too. So if we were to graph it, let's look at when she hits the ground. Right there, 60 seconds in. Well, let's graph her right in the beginning. Where is she on 0? she's getting on at a height of 5 meters. So there must be some ladder going up. And right here at 5, 0 time, so 0 time, she's at a height of 5. And then at time 20, she reaches her max height. So it takes 20 seconds to reach her max height of 10. That's a slow Ferris wheel. Oh, yeah, there we go. At 40 seconds, she comes back to 5. So 20 more seconds, her Ferris wheel's gone up and come back down to 5. At 20 more seconds, it has come back down to 0. So that's at 60. It comes back down to the bottom. Yeah, so she's getting up on at the height. And then finally, at 80, it's back to her starting point. At 80, it's back to her height of 5. And that's a complete curve, because any sine curve that comes back to the starting position is one period. That means that this is the total time it takes for her to go around. How much time did it take for her to go around? From 0 to 80. What was her max height? 10. What was her minimum height? 40. Which means I have a sine curve that's been raised by 5. Because the axis is 5. And her amplitude from 5 to 10 is 5. So it means it's stretched by 5. So I have something like 5 sine x plus 5. The period, since she starts at the bottom of her curve, that works fine. There's no phase shift. But her period is not 360, it's 80. So how do you turn 360 into 80? You divide it by what? Well, a good cheat is to take 360 and divide it by 80. And you discover that you have to divide it by 4.5. Which means this period is 4.5 shorter, compressed by 4.5. Which means I'm dealing with something that's this, 5 sine. And I wouldn't put 1 over 4.5 here, because I do the opposite. I would do 4.5 x plus 5. So 5 sine x. So it says draw a graph. Okay. What is the domain? Well, we did the domain. It goes on forever unless, well, if a right ends here, the domain is from 0 to 240 seconds. So domain is 0, smaller or equal to x, smaller or equal to 240. What is the range? Well, she never goes higher than 10 or lower than 0. So the range is 0 is smaller or equal to y is smaller or equal to 10. And since we're talking about height and s, it's smaller or equal to time for domain, and it's smaller or equal to height for range. Is this a relationship a function? Yeah, it's a sine curve, so it's a function. Another student sketched the graph but used height as an independent variable. What does his graph look like? His graph looks like it's on its side. So he put his height on the x-axis, which means the person's time is fluctuating like that. Or sorry, the person's, yeah, as their height goes up and down and up and down, the time just keeps going up. And that is not a function. Is the relationship in part of a function? No, it's not. So just to see if I got the translation right, f of x is equal to 5 sine 4.5x plus 5. And we've got to turn, that not into, we've got to turn it in degrees. And we've got to make this x-axis 0 to 240 and the y-axis from 0 to 11. Okay, so this should be our ride. Sure enough, she gets on at 5. After 20 seconds, she's at 10. After 40 seconds, she's at 5 again. After 60 seconds, she's at the bottom. And after 80 seconds, she's gone back to her height. And then it repeats again until she finishes her ride. And in this case, I've got to put a domain limitation 0 is smaller or equal to x smaller or equal to 240. And then she finishes her ride at 240 right there. And there you have her ride and her formula. And I was able to come up with the formula by knowing how much her amplitude was, how much her ride was raised off above a normal sine curve, and figuring out the new period. I knew one complete cycle was 80, and to get 360 down to 80, I had to divide by 4.5, but of course it's the opposite that happens in front of x, so I have to put a multiplier 4.5 in front of x, even though it divides by 4.15. Essentially the reciprocal. I have to put the reciprocal in front of x. And since I was dividing by 1.45, the reciprocal is 4.5 over 1, which is the same as 4.5. So that's what I put in front of x. How did I know to divide by 4.5? Because 360 divided by 4.5 becomes 80, which is the period I knew her ride did one complete cycle in. To figure that out, I took 360 and divided by 80, and that spat out. These three numbers are always going to be related, so you can use two of them to figure out the third, always. And then just test to make sure you're right. Okay, next one. How many more are there? Oh, quite a few. Oh, I don't know if I'll do it. Consider what happens to a relationship when the coordinates of all its ordered pairs are switched. That's called an inverse relationship. So the quickest way to study that is to take something like a parabola. That's not a good example. Let's do y is equal to 5x plus 3, a line. And yeah, it's distorted because I'm back in the circle. There we go. And now all I do to reverse that is change the x and y's. And that is called a reciprocal. And the reciprocal reflects perfectly through that line. So it doesn't matter what thing I do it to. I can do this with a parabola that looks like that. And I simply change the x and the y values and get the reciprocal. This purple is a reciprocal to this green. And you create what's called an inverse function. I shouldn't say reciprocal. Inverse function. And the inverse function is always mirrored through y is equal to x. It doesn't matter what function you do this for. You will create the inverse function. And you might say, how's that mirrored through x? Well, they're on opposite side of the mirror, except where they cross. No matter where I am, they're on opposite sides of the mirror. Their x and y values will switch perfectly. So at this point, let's say, I'm going to have 0.608 comma 0.37 on the other one. There, see? They have exact opposite through the mirror, the black mirror here. Inverse functions are when you switch the x and the y coordinates exactly. Explain why a relationship that fails the vertical line test is not a function. That's because you have one value of x that leads to two separate values of y. Therefore, it's not a predictive model, and it's not a functional model. Consider a relationship between x and y that consists on all points such that the distance from x and y to the origin is 5. That would be a circle. And it would be like this. So all these points around the circle are exactly 5 radius from the circle. That's the whole point of a circle. And so if he asks us, is 4, 3 on the relationship? Let's find out. We could prove this using Pythagoras' theorem, by the way. Or we can just use a table. A lot easier. Let me use a table. What if I do it like this? Nope. Okay, I'm going to do it like this then. Okay, and then I'm going to take a table of that. And then I'm going to just punch in their questions. Is 4-3 on there? Let's just see it. Let's call this one g of x, actually. And then I'll just do f of 4. 3, yep, 4-3's on there. Is f of 1 on there? Nope. And that makes sense because you couldn't have that 5 distance away. Is the relationship a function? No, it's not. The only way your x, y's can always be the same distance from origin is if you've created a circle. And circles are not functions. Notice I had to do two different functions, one with a minus sign, one with a plus sign to create a circle, if I had to do it in terms of a functional equation. Okay, the table lists ordered pairs 0, 3, 1, 4, 2, 5. So let's see. Square plus 1, no. 3, 12. Now you can have Desmos calculate this for you, by the way. You can do a table, and you can go 1, 2, 3, 4, 5, and then you can put in those values that are being asked of you. 3, 4, 7, 12, 19, 28. And you can get a good idea of what it looks like. Looks like a parabola. Now, you can also, I believe, there's a way to ask it to simulate it. But let's just try to work with what we got. Did we get a 0 value? Did we get a vertex for this? When x is 0, y is 3. There is a 0. So I've got to do another one here. Oh, maybe I got it wrong. No. And when 1, 4, 7, 12, 19, 28. So there's the vertex, which means I'm dealing with something like this. Okay, and it looks like I am stretched on the y, on the x. It's fatter on the x. So maybe a half x squared? No. There's actually a way to figure that out. 2, no. Let's half it. Close. Third? No. So interesting. Did I get my values right? Let's do old school, because obviously I'm making a simple mistake because I'm tired, I think. So old school says I can take these values like this, and I can say when x is 0, y is 3. When x is 1, 2, 3, 4, 5, y is 4, 7, 12, 19, and 28. I can can say the difference here is 1, the difference here is 3, the difference here is 5, the difference here is 6, the difference here is 2, 2, 2, which means we're dealing with an x squared. Since we're dealing with f of x is equal to ax squared plus 3, and we know that when x is 1, we're going to get a plus 3 is equal to 4. And when x is 2, we're going to get 4a plus 3 is equal to 7. Since we now have two equations with a in it, we can say that a up here is equal to minus 1. No, that's not right. I'm close here. I've just screwed something up, that's all. 1, 3. X squared plus 3, so that's right. We can say that when x is 1, this is 4. Yeah, that doesn't work though. I don't know if I can use that one. Is this it? Let's try it. When x is 0 is 3. When x is 1, it's 4. When x is 2, it's 7. Oh, I'm stupid. When x, that's it. So that should have fit. So what? Oh, God, I'm stupid. Sorry. Oh, yeah. That is how you solve it, what I did, and I just showed that I did a graph incorrect. So that's the formula. By the way, how you do that is once you figure out the difference of squares, you know it's an x squared because it happened in the second one. Then you use your base formula and you use the x and y values, plugging it in there, and then you should be able to solve a. Once you solve a, you can then have your formula. The same for x cubed and x to the 4, but as you get up to x to the 4 and x cubed, you need more values of x and y and more calculations. But yeah, you can work backwards and solve an equation. Sorry I did that so slow, but my brain is freezing. Does g of 3 minus g of 2 equal to g of 3 minus 2, which would be g of 1, which is 4. And what was g of 3? G of 3, 12 minus 7. No, it doesn't. And are they asking us why? I don't really care why. Explain. I don't know what to tell you on that one. Because it's exponential. The factors are 4, 1 and 2. The sum of the factors, 1 and 2 is equal to 7. The sum of the factors is called the sigma function. Therefore, f of 4 is equal to 7. No, don't care. Make a concept map? No, don't care. Extending. Well, this one is a function because it's only the top half of the circles we saw. And this one is not a function because it's a circle. The domain range of this is minus 5 is smaller or equal to x, smaller or equal to plus 5, and same with y. The domain range of this, our y is only between 0 and 5, and x is between minus 5 and 5. Yeah, so if it passes the vertical line test and you take the inverse, it won't pass the vertical line test, and vice versa. So this I don't really care about. This would be interesting. But it would take me longer than I want to go into. I don't know if it's that important. So that's good for chapter 1. If your teacher wants you to do the more T version ones, work with him to do it. I'm going to just show you the basics of functions in this. Okay, I hope that was super long, but I hope it was helpful.